So the rest of the lecture is going to be all about photovoltaics. And this is a technology that has changed quite a lot over the last decade. And even since I started writing this course, started giving it 2011, there's been quite substantial changes in photovoltaics. But as you'll see, there's maybe not as much in terms of efficiency changes that have happened. And we'll also explain where the technology is going and opportunities in it for the future. But this is one example of a solar farm. And this is in Portugal. You can see basically fields full of photovoltaic cells and modules. And in fact, there's 52,000 photovoltaic modules in this solar farm, and that's 11 megawatts. So if you remember, there's 1,000 watts per meter squared maximum available, and you'll see by the end of this lecture, the sort of conversion efficiencies that the best solar cells now do. Now, I'm aware that not everybody in this course will have gone into semiconductors in enormous detail. And all you need to know for this course about semiconductors is that you have a conduction band, you have a valence band, and basically the electrons fill up the valence band in a semiconductor, and there are no electrons in the conduction band normally in a semiconductor. Now we can change, if this is silicon and we add some impurities, we can have electrons being donated into the conduction band, or we can end up capturing electrons and having holes in the valence band. But what a hole is basically where an electron from the valence band is excited into the conduction band. So for a semiconductor to absorb light, what is happening is a photon of energy comes in. And if that photon of energy has an energy greater than the band gap, it can excite the electron from the conduction band, from the valence band into the conduction band, and it leaves behind a hole where there isn't an electron anymore. This is said to be electron hole pair generation. So the photon comes in, you can basically generate an electron in the conduction band, and you leave behind a hole in the valence band. Now, actually, silicon, it's a bit more complicated. But for gallium arsenide, the bottom of the conduction band and the top of the valence band end up having the same wave number for the electrons. So there's a quantum mechanical property, and I don't want to go into too much detail, but the wave numbers basically all happen where the wave number is 0. When we've got silicon, the bottom of the conduction band and the top of the valence band, there's a difference in this wave number. So this h bar k, so Planck's constant divided by 2 pi, times the wave number of the electron. And this h bar k is a momentum change. So it's not just a photon we need to be able to absorb, to be able to excite an electron from the valence band to the conduction band. We need some heat. And the quantized form of heat, which is just the atoms and the lattice of the silicon vibrating, they vibrate in particular modes. The way this is calculated is just thinking the atoms are connected to each other in springs. Those springs are the lattice vibrations. And by modeling that, we can work out this K value, and it relates to the spring vibrating. So we need some heat, and we need the energy of the photon to allow us to absorb light from the sun. So in fact, direct bandgap materials are much more efficient at absorbing photons of light because they don't need heat to convert them into electricity and to generate the electron and the hole pair, while something like silicon needs a bit of heat, and that makes them less efficient as solar materials. Now we'll talk about how much of an efficiency difference that actually is a little bit later in the lecture, but that's the basics you have to understand. So how do we build a photovoltaic cell to generate electricity? Well, there's 3 main parts to this. The first is we need a semiconductor with an energy band gap that we can absorb the energy of the photons and excite an electron hole pair. We then need to separate the electron in the hole. If we don't separate them, this electron can always fall back down to the hole and it emits a photon of light. So when the electron falls down and emits a photon of light, this is a light emitting diode, or if you put this in an optical cavity, you make a laser. So that's the difference between these things. It's a photodetector, or a photovoltaic cell absorbs photons and creates electricity. Light emitting diodes and lasers take electricity and emit photons of light. So we just need to apply an electric field. And to be able to do that, we need to have electrical contacts, but also this is a current that flows with the electrons flowing in one direction. And so that builds an electrical circuit. We need the electrical contacts to connect to the outside world, to a load, to consume the electricity, or we can have a battery that we charge up or put it on the national grid. So you can see we need something that absorbs photons, something that separates the electron-hole pairs, and something that collects the current. Now actually this separating the electron-hole pairs, we can build in an electric field into the photovoltaic cell, and that's typically what's done. So without going into too many details, but if we pick different semiconductors or different materials such as metals, where the bands align are all a little bit different depending on the electron affinity or what's known as the Schottky barrier height. So if we put a metal down on top of a semiconductor, it will bend the bands, and this band bending induces an inbuilt electric field that separates the electrons in the holes. Now the problem is there's only a few metals that are transparent at the wavelengths of interest, and in fact these are not very efficient because it's a small electric field, and so Schottky barriers are not really used for photovoltaic solar cells. What is done is that we put impurities that donate or capture electrons, creating holes in the valence band, and we put them beside materials that we put in impurities that basically donate electrons up to the conduction band. And the first one's called p-type, the second one's called n-type, and due to equilibrium, again, you don't need to know so much about this for the course, but what it does is we need to have the average energies in both the same, and that creates a difference that we end up with this built-in electric field, what's known as a p-n junction. And so in the gradient between these two, we end up with a strong electric field that separates the electron-hole pairs. Now in most semiconductors, the doping you need to do this well and have low resistance losses means that this distance is probably only going to be 100 nanometers for absorbing. So instead, the way that actually real photovoltaic materials and cells are built is that they have the p-type at one side, the n-type at the other side, and then in between they have a nominally undoped, or what's known as I for insulating or undoped. And this gives you potentially, in fact, in some cases, millimeters of absorbing material. Most cells, this is typically actually 100 microns or so to actually absorb light. Now, I'll talk in the next slide exactly how much you need to be able to do this. But as you can imagine, you need this area to be thick enough to absorb as many photons as you can capture from the sun. Now, in fact, both of these have the same equations, and we'll talk about that a little bit later over how we can work out the current and the voltage for these systems and work out what the maximum efficiency is. So which semiconductor material are you likely to pick? Well, there's a whole series of issues around this. And of course, there's cost, how cheap it is to fabricate photovoltaic cells. But the first thing just to think about is that with the different materials, they can absorb light at different parts of the electromagnetic spectrum. So if we look at gallium phosphide, it's extremely different to gallium arsenide, indium phosphide, silicon, germanium, and so on. Now, if I put on top, this is the black body of the sun, you can see here's red, green, blue. so the visible part of the spectrum. And silicon actually absorbs the whole of the visible part of the spectrum. So does gallium arsenide. Germanium saturates a bit. So you can see silicon is actually used for a lot of digital cameras, and certainly the cameras in all smartphones these days, because it's cheap, you can mass manufacture, but it covers the whole of the visible and a little bit to longer wavelengths than the visible as well. Now, actually, gallium arsenide would give you better efficiency if you were to make solar cells in it rather than silicon. But it's about a factor of 200 times more expensive than using silicon. So most solar cells at the moment are made out of silicon. That's because it's a relatively efficient photovoltaic material, but also it's extremely cheap. So in terms of price performance trade-off, silicon is one of the best materials for photovoltaics at present. Now there's many others that people are researching, trying to reduce the cost, trying to improve the efficiency, and we'll talk about that later in the lectures. Now here what I've plotted is the absorption coefficient. This is basically the 1 over E distance that an average photons will go into a material. And if we turn it around, this gives you the light penetration depth. So from this, we can basically work out how thick you need to make a material to absorb a certain number of photons. So this will determine how thick material you require to absorb all the solar energy that impinges on a material. Now, the other thing from an engineering and manufacturing perspective, you want to minimize the material in a photovoltaic, because the more material, the higher cost. So all these things have to be considered when you're picking a material to actually build a photovoltaic cell. So let's calculate the actual equations so we can work out the efficiency for any photovoltaic. Now, the electrical engineers and some of the physicists will probably understand everything I'm going through. You just need to use the equations that are here. I'm not going to derive the Shockley equation for a p-n junction. You can just quote it out the lecture notes when you need to use it in exams. But there's enough here to at least allow you to calculate for any photovoltaic cell the efficiency. We need to start with what's known as the superposition approximation. And what we have for any photodetector or a photovoltaic cell is that if there is no light shining on the cell, we're still going to have some current that actually flows through the circuit that we have. And that's known as dark current. Now, for the people that understand the electrical engineering circuits that I'm doing here, that's normally modeled as just a diode in the circuit. So we have this diode that there's going to be a current flow even without any light shining on the photovoltaic cell. So it's pretty close to a current density of 0. And because of the p-n junction, this falls off to negative values of current if we go to larger bias voltages. When we shine light, what we get is we're going to get a light, a current that looks like this as a function of the bias voltage across the photovoltaic cell. So this is modeled as a current source. And so this is the equivalent circuit diagram we actually use for the modeling. We use what's known as the superposition approximation, that we can have the compact model here that is just the dark current plus a current source for the photovoltaic generation of electricity. So we generate a current every time a light shines on it, and that will happen up to a particular voltage that's known as the open circuit voltage. So if we don't connect this to a load or to a battery, this is open circuit, and that's the voltage we measure here. If we short the two ends between our positive and our negative, that's the short current that we measure at this point, because we'll get a voltage when we short this of 0. So this is our short circuit current density that's basically a bias voltage of 0 at this point. Now the superposition approximation is that the actual current density that we measure as a function of voltage is the current density at the short circuit point at V equals 0 minus the dark current. So for instance, if I want to know the value here, the actual currents that we have flowing in a load or in a battery that we connect to this would be this value minus this value for a particular voltage on the circuit. So now what I want to do is just give you the equation for the photovoltaic cell that we need to be able to do the dark current. So just turning around what we had in the last, we basically got that the current density, capital J here, is the short circuit current density minus the dark current. Now the dark current is given by what's known as the Shockley PN diode equation. So as I said, you can look this up in textbooks. I'm not going to go and derive this from first principles, but it's given by, or the dark current is given by a constant times an exponential, which is the electron charge, so 1.6 times 10 to the minus 19 coulombs, times the voltage divided by Boltzmann's constant, so 1.38 times 10 to the minus 23 joules per Kelvin, times the temperature, minus 1. So you just need to use this equation. You can look up any semiconductor textbook to actually see how it's derived and where it comes from. But it's for any PN or PIN diode semiconductor device. Now, to actually do this properly for a real circuit, what we also have to think about is adding series resistance and a parallel resistance in the equivalent circuit. So first we just take this and we swap it around. Well, we want to put it into this equation. So our current is now the short circuit current density minus the Shockley PN diode equation. If I want to find the open circuit voltage, then using this equivalent circuit, well, I just put in J equals 0 into here. It means I end up with JSC minus this, so I can turn this part over here. I've got an exponential QV KBT minus 1 equals JSC over J naught. So if I take the logarithm both sides, and then I take this over, I end up with the open circuit voltage equals Boltzmann's constant times temperature divided by the electron charge is the logarithm, the natural logarithm of the short circuit current density divided by this J naught from the Shockley equation plus 1. So that all I've done is taken this equation, put in J equals 0 for in here since there's no current flowing, and I end up when I rearrange to get this equation. So we've got everything we need now to actually go and define the efficiency of a photovoltaic cell. So we've got our light current diagram, and the power density of this is given by the current density times the voltage. So this is a power density because we've defined it as J. J is the current density is just the current I divided by the area. So the power would be the current times the voltage rather than the power, the power density of course is J times the voltage. To get the efficiency, it's the electrical power out divided by the optical power in. So to write that in a little bit different way, the efficiency eta is the maximum electrical power out divided by the optical power in. Now in this diagram, the maximum power density we can extract is given by what's known as the maximum power point. Now it's not that this is a rectangle. We're actually going to have some sort of curve that we have in this. Now, in fact, what you're trying to do is get this maximum power point as close to JSC times VOC, but you can never quite get up to this point. And that's because of some of the losses in the system that we have, that when we apply a load, an impedance match, there's always a little bit of impedance mismatch, some losses in the system. And so the maximum power is at Jm for the maximum current density, and VM for the maximum bias voltage we can have for the inbuilt bias of a photovoltaic cell. So our efficiency is JM/VM for this point here, divided by the optical power. Now, this is normally rearranged a little bit, because when we go and characterize photovoltaic cells, actually finding this JM and VM is going to depend on the load that we actually are powering in a circuit. Now that means that what you get varies depending on how you use the photovoltaic cell. But what are constants for a photovoltaic cell are the short circuit current density JSC and the open circuit voltage VOC. So to compare all photovoltaics, you take the short circuit current density, you take the open circuit voltage, you define a standard circuit that gives you the maximum power output for a particular impedance. And this defines this equation where what you do is you define what's known as the fill factor, which is the difference between, if you like, this point and this point. So this really is a practical way of allowing comparison between all photovoltaic cells. And as you'll see, if you look up any papers on photovoltaics, what is normally defined is the standard test conditions at AM 1.5. And we'll talk about that in a few slides. And then you're given the short circuit current density, the open circuit voltage, and the fill factor of the cell. And from all of those, you can compare how well these cells will work under different loads and different power conditions. So this is all just giving you the values and what we need. Let's look at some of these values for real materials. So you can look these up in tables, and this is just taking some standard materials. So crystalline silicon, here's polycrystalline silicon, crystalline gallium arsenide, amorphous silicon, some different organic polymers, cadmium telluride. These are all different materials that have been used for photovoltaic cells. And they all have slightly different short circuit current densities and slightly different built-in open circuit voltages. So the open circuit voltage is dependent on the band gap of the materials. And that's why these things change. The short circuit current density is a little bit more in the design of the solar cell as well. But the theoretical maximum limit, the theoretical maximum output power for any material is given by this curve here, and it's a function of the band gap of available materials. So in fact, this voltage that we have is directly proportional to the band gap of the semiconductors, and that's why we've got these different materials sort of going somewhere like the theoretical curve. So if you've got very high short circuit current density, you've typically got a bit lower open circuit voltage and vice versa. Now, in fact, one of the things to note here is the voltages are typically all less than 1 volt. Now, there's also going to be some series resistance in any photovoltaic cell. They can be made load, but there will always be some. Now, in fact, modern electronics means you can power directly with the voltages that are available. But for many of the systems, and particularly for batteries, you're going to need voltages that are substantially larger than 1 volt. So you have to stack the photovoltaic cells to increase the voltage. You also have to look at modules with stacking either parallel or in series to get the appropriate current and voltage that you want as output. And you're also going to need power conditioning to be able to power circuits with the right current and voltage. So let's look at technologies and the outputs. Now, I've been running this course for a number of years. Every year, I keep on updating this slide. But what I think is quite useful is go back to one of the older slides. And at the time, 2012, these are the world records. So not what you can buy, but these are the world records in the research community. And as you'll see here, the standard test condition for all photovoltaic cells is AM 1.5 spectra. So that's actually having the wavelength spectra of the sun with AM 1.5. So it's an integrated 1000 watts per meter squared illumination. It's at what's known as one sun. So one sun means it's basically 1000 watts per meter squared, and there's no concentration. You'll understand much more about concentration in the next bit of the lecture as we look how we can improve the values. And it's at 25 degrees C for the temperature of operating the cell or the module when it's measured. So these are standard conditions so that we can have a fair comparison between all different technologies. So silicon has a conversion efficiency of about 25%. So remember our 1000 watts per meter squared. With 25% conversion efficiency, it means that we get 250 watts for a meter square of silicon. So, if you look at Glasgow, now this is the peak power. So that's the peak you're going to get of about 250 watts per meter squared of photovoltaic cells that you have out. Now, houses typically will be a number of kilowatts that you require at any one time. So if you need to get 5 kilowatts as your power using photovoltaics, you can see that that's going to be 20 square meters of silicon photovoltaic cells if the efficiency is 25%. So that's how this works. So the best gallium arsenide was 28%. There's other technologies. You can see the short circuit current densities, about 42 milliamps per centimeter squared. Voltage is 0.7 for silicon, and the fill factor was 82%. So here's the values that were published in January this year, 2021. Well, silicon's gone up, but it's not gone up by very much. Gallium arsenide gone up, well, from 28 to 29.1. So it's gone up a little bit. Polycrystalline silicon's gone up a bit more, by about 3%. And then there's a few other technologies. Perovskites is a new technology since I started this course, and already it's got to about 21%. It's supposed to be a lot cheaper than silicon and has the potential to displace silicon in places. But the point I'm making going from 2012 to 2021 is that most of these values have not gone up by a lot. They've gone up a little bit. So there's been incremental improvements, but there's not been a big change. The other thing is that these are world records for the materials. And over time, these solar cells are out in the sun. You're going to get X-rays, you're going to get all the solar energy with the ultraviolet, high energy particles from space and the sun. And actually that puts damage into the semiconductors that trap electrons and holes, and that reduces the efficiency over time. And as I said before, anything that's solar, if you get dust falling on the surface, that reduces the amount of light that goes in. So over time, photovoltaic cells actually reduce their efficiency because of the damage from the high energy particles from the sun and from space. So here are the numbers. The biggest number we've got here for efficiency is 29%. Now remember the Carnot efficiency we spoke about, and it's 85% for absorbing photons of light in a black body absorber. So why are we only getting 29% in a photovoltaic cell when the Carnot efficiency is 85%? Well, it's because of a whole series of reasons. First, the band gap of the semiconductor. The Carnot efficiency absorbs every photon of every wavelength or every energy, if you like. Because of the band gap of the semiconductor, we're not absorbing any photons below the band gap. So for silicon, that's 1.1 eV. So there's a whole part of the solar spectrum with silicon we're not absorbing. So we're just throwing away that efficiency. Photon recycling. Well, as I said before, one of the issues is that if you absorb a photon and generate an electron hole pair, some of those electron hole pairs will recombine and emit more photons. So there's always some photon recycling, and some of the photons will be re-emitted. Generation through irrecoverable thermal energy. Well, I'll talk about this in the next slide, and it's easier to explain. But any of the photons that are greater than the band gap of the semiconductor, you generate electron hole pairs. The electrons in the holes have to thermalize down to the conduction band edge and the valence band edge, respectively. That emits phonons or heat, and that creates an inefficiency, and it reduces the Carnot efficiency from the Carnot efficiency of the system and gives you more losses. Also in the semiconductor, you've got surfaces. Some of the light will get reflected from those surfaces, and that gives you a particular loss, and so you're reducing the Carnot efficiency again. Now I'll show you in the next bit of the lecture how we can reduce that, what's known as anti-reflection coatings, but you can never get that to zero. You've always got some losses. There's a few other things. There's some internal losses. This is really where the semiconductor has got some defects. No semiconductor is completely perfect. So this reduces what's known as the internal quantum efficiency of absorbing photons. You need to make electrical contacts. Typically, you've got grid patterns for the contacts to those. That's what you see as the metal on top of solar cells. That will actually reflect photons back, and that produces a shadowing pattern that reduces efficiency. And also, we need to make electrical contacts. We've got wires connecting to our cells. The semiconductors have finite resistances. This all has dual or resistive losses for the contacts, the p-n junction, and so on. So all these mechanisms are the reason that we're so far below the Carnot efficiency. So let's just show some of these a bit more diagrammatically to try and explain what they are. So the first one was where we have the electron hole pair generated, and the photon of light has a much bigger energy than the band gap of the semiconductor. So the electron is excited to much higher energy in the conduction band, and then it has to emit heat in the form of photons to thermalize down to the conduction band edge. So this is where it gets to before it gets conducted in the system. For the hole, it's the same. Holes have got negative energy, the way this all works out. This is more simply to make it easy to use equations. A hole is a negative electron. So from that, it actually appears to go up in energy, but hole energies are reduced as you go up the page. So again, this is reducing in energy to get to the valence band edge. We get junction losses. So scattering as an electron tries to move across the junction through the background doping or defects. We get some recombination. So some of the electrons may recombine with some of the holes. And again, they're lost to the electricity in the circuit, reducing the efficiency. This has got to get out into the metal. There'll be a barrier. I've shown this as a gap, but this gives you a resistance. So I squared R will have losses here. And of course, none of the photons that have got energy below the band gap get absorbed. And that's why there's a number that's actually way below the Carnot efficiency. So how much below the Carnot efficiency? Well, both Shockley and Quasier at Bell Laboratories in 1958, after making the first photovoltaic cells in the 1950s, they tried to work out what was the maximum efficiency of a single semiconductor photovoltaic cell. And this is known as the Shockley-Quasar efficiency limit. And again, you can look up the paper in Journal of Applied Physics if you want to go through this in detail. I'm not going to derive it because it's quite a long paper and quite complicated. You just need to know the answer. And that's all we're doing in this course. So it's important because it really is the maximum you can get out of one semiconductor material and a real photovoltaic cell as it's used. So it considers a cell with no light and no applied voltage. It assumes that the cell emits as a black body. Now, in fact, what this is doing is assuming that all the photons that impinge on the cell that have an energy that are greater than the band gap are absorbed. It attributes all the radiation to energies to be band-to-band recombination. So basically any photon coming in above the band gap of the semiconductor is absorbed and gets turned into an electron hole pair. And then what it does is it also includes the angles you might have in terms of collecting the photons. This is important because if you get photons coming from different angles, in reality, this black body emitter emits over a complete sphere. But actually, most photovoltaic cells are flat and two-dimensional, and we're only absorbing light from one direction. So we need to have a solar intercept fraction to account for that. And then the final thing is you can also look at the rate of recombination. That's basically, again, saying everything's band-to-band. And actually, none of the electron hole pairs recombine for losses like that. So if we take all these things, in fact, what the theory comes up with is depending on the temperatures and the band gap of the material, you get a maximum efficiency known as the Shockley quasar efficiency. So for silicon, that's 30%. And as you've seen, the best silicon photovoltaic cells are 26.7%. So actually, they're pretty close to the Shockley quasar limit, assuming all the photons are absorbed above the band gap and recombinative losses are very low. For gallium arsenide, it's 31%, and the gallium arsenide record is 29.1%. So again, it's pretty close to the theoretical efficiency for this type of solar cell. Now you can do this as a function of the band gap of the semiconductor material, and you can see that the efficiency varies. And in fact, gallium arsenide and silicon are pretty close to the peak of efficiency of photovoltaic cells. So this is pretty good. And what I'm going to do is show you a number of the tricks you can do, first to get these very high efficiencies that are close to the Shockley quasar limit, but also how we can go higher than the Shockley quasar limit. So the last part of the lecture, after we have this break, is going to talk about what can we do to improve the efficiency above the sort of 30–31% that Shockley quasar has defined as a maximum. So at this point, I'm going to stop and take some questions. So we'll just stop the recording.